This video discusses about the evaluation of the fit of a GLS model. Let us first recall the procedure in the case of a OLS model. First, the assumption about the mean of residual errors is 0 was evaluated by exploring whether the mean of residuals EI hat, so the empirical residuals, has trends with respect to yi or any of the predictors. And it's important to notice that here the y is the y hat, so it is we should look at the trends with respect to fitted values and not true values, observed values of y. And then the second assumption about the constant variance of residuals was explored or evaluated by exploring whether the variability of the empirical residuals seems to be constant with respect to fitted values or any of the predictors. And the assumption that the covariance between any pair of residuals is 0 was evaluated by using appropriate graphs depending on the potential region for the non-zero correlation. And in the case of repeated measurements over time, we used the autocorrelation function, so that was the example we used in the stump lift data, where we had some reason to assume that observations that are close to each other in time are correlated. And now it's very important to recognize that in the GLS model we use the same data as in the OLS model, and heteroskedasticity and autocorrelation are properties of the data, and therefore they never disappear when we switch from OLS model to GLS model. But we need to check whether the models we assume, so whether the power type variance function or AR1 structure for the residual for the autocorrelation structure, whether these models really fit to the data as we expected. And we need tools for that. But so the important point here is that if you look at the residuals of a GLS model using the raw residuals E hat of the GLS model, you will see the same heteroskedasticity and autocorrelation that you saw in the OLS model. But that does not tell anything about the model fit. But we need some additional tools, a different kind of residuals to explore the fit of a GLS model. So we define two new residuals. The first one is the person residual. It is sometimes called also standardized residual, but actually the standardized residuals means slightly different thing in theoretical statistics, so it's better to call it person residual. So we denote this person residuals by E tilde I, and it is defined by dividing the raw residual E hat I by the square root of the estimated variance of residual errors. And now, because this F variance function allows heteroskedastic variance, we are actually dividing the raw residual by its estimated standard deviation. And for example, if we had the power type variance function, then this variance we use in this definition is the one based on the power function we used using the Dremel estimates for both parameters of the variance function. And if this variance function we have fitted models satisfactorily the non-constant error variance, then these person residuals should show constant variability with respect to fitted value and all predictors of the model. Then the second type of residuals we define is the normalized residuals. For that purpose, we define matrix gamma such that this matrix product gamma gamma prime is equal to matrix C hat, and this C hat is the estimated correlation matrix of residual errors. So in the OLS model, this C matrix would be simply the identity matrix, and in the GLS model, where we assume constant error variance, so it means the GLS model where we only model the dependence of the data, but the assumption about the constant variance is kept as it is in OLS model. In that case, the C matrix is equal to the V matrix. And in linear algebra or in matrix algebra, this product gamma gamma prime is called the Cholesky decomposition of this C hat matrix. So if you want to learn more about that, you can try Google using this keyword. And the normalized residuals E I, and I'm using dot on it, so E dot I are computed from person residuals E tilde I by using the following formula. So we take the inverse of the matrix we formulated using Cholesky decomposition and pre-multiply the person residuals by this matrix, and then we get the normalized residuals. So these matrices, these residuals cannot be specified in the scalar form, but we need to compute them simultaneously for all data, because we need to use this matrix for computation, and that is clear because we are actually modeling the dependence among the residuals, so we need to know all the pairs before we can do anything. That's why this is defined only in the matrix form. And if the Cholesky assumption, Cholesky decomposition was based on the true correlation matrix of the residual error, so if the correlation between the person residuals is this C matrix, then these normalized residuals have correlation I. So the normalized residuals are not correlated anymore. And that is the key for evaluating the assumption about the correlation. So we explore whether these normalized residuals have any correlation. And then if they don't have, then we know that the correlation model was properly or satisfactory in our case. So if the assumed correlation model, such as AR1, was satisfactory, then the normalized residuals based on that model should not be correlated. And therefore we should check the autocorrelation function of the normalized residuals in that case. And if we were working not with the temporal data but spatial data, then we should formulate the dependent structure using some spatial variogram, and then if we want to evaluate whether that fitted to the data, then we should compute the normalized residuals based on the fitted spatial variogram model, and to explore the fit of that model, we should see whether the normalized residuals based on the fitted spatial variogram show some spatial correlation, so we should explore them spatially. And about the group data, we will learn more in the later lectures of this course. So let us now summary how you should check the model assumption of the GLS model. So again, the most important assumption is that about the mean, and the procedure for that is the same as before, but you can use either the raw residuals, person residuals, or normalized residual. It doesn't make a difference, and you explore the trends in the mean with respect to fitted value and all predictors. So quite same as before, and you can use either of the residuals. And then the assumption about the variance of residual errors. Now we, in this case, we separate the assumption about the variance and correlation because they are explored in different way. So first about the assumption about the variance function. And in this case, you can use either the Pearson residuals or normalized residuals, but we cannot use the raw residuals, and you should explore whether the variability is constant with respect to fitted value or predators. And the third thing we need to explore is that whether the correlation between EI and EA prime is as it was assumed. So, for example, in the AR1 case, it follows the AR1 process. And in this case, we use the normalized residual, and we should explore whether the normalized residual shows some correlation structure according to the structure of the data. And then the fourth assumption about the normality, we should use either the Pearson residuals or normalized residuals and check the normality using QQ plots. So for the QQ plots, we should not use the raw residuals either, if we have assumed some variance function for the data. Now let's look at example. So there was example 1.10 in the lecture material. We already looked at the original OLS model was evaluated already previously, and it was found that in this graph it was found that there might be some signs of heteroskedasticity, and also this autocorrelation plot showed that we might have some slight temporal autocorrelation in the data. And in the previous videos we already fitted the GLS model to the data that both assumed the heteroskedastic variance and autocorrelation, and they were called mod 2. So mod 2 included the variance function for the residuals error but no autocorrelation structure, and mod 3 included both autocorrelation structure and heteroskedastic variance model according to the power type function. And we can now explore whether the model fits. So first we plot the residuals of model 2, and now we need to specify, this is very important, we need to specify that the type of the residuals is the Pearson type residuals. So then we are computing the ones we presented on this video. So then we could look whether the variance function fitted, and then when we plot the autocorrelation function of model 3 to explore whether the AR1 structure properly fitted model the autocorrelation structure, we need to specify here that residual type is N. And we could also use this alpha 0.05 to really show the confidence limits for the autocorrelations. And then we could also make the QQ normal plots about the residuals by using these commands. So here we see the residuals. So here we have the Pearson residuals. It says that they are standardized, but they are standardized residuals of the Pearson type, and they are with respect to machine. And now we see that when we fitted the variance function that included diameter, it also makes the variance constant with respect to machine. So this was explained by the fact that the range of diameters, so the biggest trees come mostly from the same machine. So therefore the machine that has highest variance in the previous graph actually has also the biggest diameters. And now when we look at the residuals with respect to diameter, we see from this graph that the variability is roughly constant, and when we use this viscous plot where each line shows the variance in for example this line here shows the variance within this window and so on, we see that the lines are approximately of the same length, so it seems that the variance is quite constant. And then when we plot the residuals with respect to fitted, we see the same issue also here, same thing here, so there seems not to be any heteroscedasticity in the Pearson residuals. And finally, here is the autocorrelation plot on the here about the model where we used the model 3, and we see that now at lags 1, 2, and 3 the correlation is very weak. We still have some high correlation about 0.05 level at lag 4, but okay, it's the only case where we go beyond the confidence limit, so it's not serious, and I would say that we are satisfied with this model. Maybe in time series, if this time series correlate or this correlation structure would be of our primary interest, we could still try to make a more advanced model, but because this is just a nuisance in our case, we are very much satisfied with this correlation structure or this correlation model based on AR1 process. And finally, here is my normal QQ plot about the residuals of the normalized residuals of the final model. This is not very good, so we see, for example, that for theoretical quantile -3, we have the empirical quantile is only -2, so we have very short tail in the left hand side. On the other hand, for theoretical quantile 3, the true empirical quantile is somewhere almost 5, so we have very heavy right hand tail. So it means that the residual errors, if we plot the histogram of the residuals, it looks like this. So the density looks something like this. So we have quite light tail on the left hand side, but heavy tail in the right hand side. But these methods, even though we needed the assumption about the normality in fitting of the model, it is actually quite robust to the discrepancies from the normality, and therefore I would not be that much worried about this issue. We still have modeled the variance and covariance properly, and therefore we are quite satisfied with the model. If you want to learn more about model assumptions, you could read the book by McCullough, Searle, and Neuhaus. The textbook, it includes a book chapter about these problems. So our conclusion was that this model 3 is satisfactory in this case. And then the bit with respect to this, or the discussion about these outliers or influential observations, we should also look at them using the same way as we discussed previously. And also this multicollinearity is a similar problem in GLS model as it was in OLS model. But nothing has been changed on them, so you should just recall what was explained in the previous video about them.